afternoon. My name is Francisco Igual from Universidad Complutense de Madrid. I am presenting today our work applying game learning environments to power capping scenarios via reinforcement learning on multi-cores. This work orbits around the concept of malleability. Malleability understood as the ability of both applications and architectures of modifying some of their knobs and hence some of their behavior at runtime. Some examples. In terms of applications, the dynamic selection modification of the number of threads that an application is executing is commonly referred as malleability. But there are more knobs, some of them application specific, in all applications that have direct implications in output metrics and that can also be tuned at runtime while the application is running. In a similar way, modern architectures, are also malleable. For example, DVFS can vary the frequency, the operating frequency of the cores, and hence has an impact both on performance and energy consumption. We can disable or enable cores as they become necessary or unnecessary for execution. Some levels of cache can be partitioned at runtime, etc. In general, as said, both applications and modern architectures are malleable. In addition, there are different optimization goals depending on the specific scenario. For example, energy efficiency, performance maximization, or quality of experience are output goals that usually in an isolated manner or in common can be optimized. Finally, there are some additional restrictions that in some scenarios can also be applied in terms of applications or architectures. For example, power capping is one of them, but other application-specific parameters, for example, quality of service, can also be limited to attain a minimum acceptable quality of service, for example. Our challenge here is to investigate on this question. Can we obtain common policies that mix different knobs or optimization goals? We think it is possible. Historically, this problem has been tackled in terms of programming by hand some set of heuristics that apply this malleability logic. These heuristics can be embedded into applications or runtimes, but they have some pros and some cons. The first one is that no training is required. An expert in the application can program these heuristics by hand, and without observation, they can work out of the box. They are usually very simple and understandable for the expert in the application area. However, it has some drawbacks. For example, all these conditions are fixed, and they are usually quite simple. They also depend on problem inputs, and obviously, some expertise in the problem is mandatory to program them. The second option is applying machine learning techniques. In this case, our goal here would be to design or derive automatically malleability policies and learn them by observation. Observation applied at runtime. The pros here is that no problem knowledge is necessary, or at least not as much problem knowledge as for the heuristics. And all these policies can be input independent, so they can work for any input for the problem. The drawbacks here is that the extracted policies, as all policies applied or extracted with machine learning, can be difficult to explain, and also long training periods, as this is usually extracted at runtime by observation, is required. Our proposal is to apply reinforcement learning, that is the second option, for a joint architectural and application malleability by leveraging and using existing machine learning infrastructures. Specifically, some of them, the definition of the environment and definition of the learning agents, are extracted from another arena, that is the game learning scenario. This is the outline of the presentation. We're covering some brief concepts about reinforcement learning. Then we will see how can we tackle the problem by modifying existing environment creation infrastructure and agent creation infrastructures, and see some experimental results for a specific problem, that is power capping in this case. And we will finish with some conclusion and future work description. The goal, as said, is the use of reinforcement learning techniques to take control of energy consumption of a server or a processor through changes in its execution frequencies. We want to leverage existing game-oriented software infrastructures and to apply software power capping restrictions. Power capping is a well-known method employed mainly in data centers that allows to limit the power being consumed by the servers, obviously with implications in performance and energy efficiency of the running applications. RL, or reinforcement learning, is one of the basic models of machine learning besides supervised and unsupervised models. It is oriented towards the training a system to be able to automatically determine its behavior, optimal behavior, to maximize a score based on rewards. Actually, what we have here usually is an environment that is interacted with an agent or a set of agents. This agent just applies continuously actions for a given environment state and receives a reward in exchange. Building a policy or learning is to build a probability distribution of actions. That is the probability of selecting an action A in a state S that maximizes the expected accumulated reward. Typically, this has been tackled from the computational perspective in terms of tables that store in each one of its cell how good or bad a given action or the application of a given action is at a given state. This has some limitations. First of all, scalability, specifically as the amount of pairs grows. And second, the usage of system resources, the system that is being trained itself, for example, to build or to look up in these tables. A typical solution here to mimic the behavior of a table is to use function approximators, specifically use DNNs as a function approximator. Here, the training of the DNN is the exploration, the build of this type of tables, and the inference process on a training network is what we call the exploitation phase on the reinforcement learning. That is, look up the best action for a given state. This proposal, based on neural networks, has some benefits. The first one is better scalability. Training and inference on a network usually scales well with modern hardware. And second is the use of domain-specific architectures. In our scenario, this is very interesting because DSAs are independent from the application computing resources. They're available and cheap, and we can build a knowledge base to perform model portability. That is, we can build a model here and port it to any other machine. Historically, reinforcement learning has been applied for game learning. In this case, the environment are the sequence of screen captures that can be observed in a game, and an agent interacts with it, extracting characteristics via, for example, convolutional layers on a neural network, and applying or building policies to maximize rewards. For example, in this case, we have a typical, very simple video game in which we need to land a spaceship in a given spot between two flags. The first one is just an environment taking or receiving random actions. But after 100 training steps, applying random actions and getting rewards in exchange, we see that the behavior of the player, automated player, is improving. And after 600 training steps, we can see it has learned how to play. Our goal here, or our approach, is to mimic this behavior using reinforcement learning, using exactly the same software infrastructure, but adapting the environment to our specific scenario, that is power capping on multi-core. Going a little bit back to reinforcement learning definition, we have an agent that interacts with an environment. The agent applies actions randomly or learned and received a new observation and a specific reward. Applied to game learning, there are four main actors here. The environment is modeled or abstracted through a piece of software in Python called Gym. We will talk about Gym in a moment. But basically, it defines an observation space, an action space, and how the rewards are modeled for this specific environment. The agent is usually deployed in terms of a software that applies or implements optimized algorithms for training and inferencing. In our case, in game learning, we will use RLlib as the software infrastructure. The received observations here are just screen captured images. This will be the input of the neural networks applied by RLLib. And each action will be just a game movement from the virtual player. For example, move up, down, left, or right. How to apply this to our power capping scenario? Well, we just need to define our own environments in terms of observation space, action space, and rewards. We can leverage exactly the same training based on neural networks that apply it for games, but obviously, observations will be, for example, energy or power measurements via RAPL. And actions will be applied to the architecture to modify frequency, for example, via CPU frag. All in all, we have the same infrastructure, just interacting in a different way with the environment. The first software infrastructure we are leveraging here is GYM. OpenAI GYM provides abstractions for environment creation. It just abstracts away an environment and builds it as a black box with a very trivial API. First, a reset function that obtains an initial state observation from the environment, and second, the important one, a step function that applies an action by an agent and observes the changes in the environment. This type of environment completes the API by returning to us two main pieces of information. The first one is an observation, that is an object that represents a new observation after the application of an action. It is defined by the user, the type and range of values that an observation can take. The second one is the reward obtained after the application of a new action, and it is also defined by the user. Internally, each environment features an action space that defines which values can be taken as actions, that will be the output of the neural network, and an observation space that will define which values can be taken as observation, that is the input to the neural network. All in all, obtaining a suitable reinforcement learning policy is just the task of training the underlying neural network by observation and interaction with the environment. This process can be transparently carried out by the RLLib framework by means of interaction with the GYM environment. RLLib is a library or an infrastructure for RL deployments. It implements a big number of reinforcement learning algorithms, agents, and handles all the interaction with the environment. The advantages are multiple. It is very mature, it is scalable, can be used as a distributed platform across different nodes, for example, for training processes. It abstracts away the complexity of the environment, and it can be trained via GPUs, for example, for acceleration and not interfering with the existing platform, and it is based on neural networks. It is important here to note that for games, we have CNN with some feature extraction layers, convolutional, and then fully connected layers for classification. And here in our environment, as we do not have screen captures, we will only have these fully connected layers. The next step in the presentation is to explain how to create an environment that adapts game learning scenario to our power capping scenario. The first environment, ENV1, is a very naive environment for power capping. First, we define a target, power, and establish it as a power cap. And we define both an observation space and an action space. The observation space is defined as a finite set of power intervals with an homogeneous distribution in this environment. We need to decide here how many intervals and how big they are. This is ultimately a trade-off between accuracy and training or exploration time, as if the power intervals are smaller, that is, there are more power intervals, we need more time to explore all of them. The action space is very simple here. We just define two actions. One is increasing one step the frequency of the processor. The second one is decreasing one step the frequency of the processor. And the rewards are designed to maximize performance without violating the established cap. So we define a negative reward if the new observation is farther from the target previous one, and positive rewards if it is closer or it is in the target power interval. Let us take one clear example and demonstrate that our environment can learn that if a specific power cap is established, for example, in our case, 52.5 watts as the power cap, We need to learn, or it needs to learn, that 1.6 gigahertz is the specific frequency that must be fixed. We have trained or tested different workloads. This specific point, marked in red in the figure, is for a double precision matrix multiplication, sequential. First of all, does the environment learn correctly? This is a representation of the training process of an agent interacting with this environment, M1, and a target power of 52.5 watts across different epochs. As we see, we are representing here the accumulated mean error as the training process evolves from left to right. And we see that after 4 epochs, we are already establishing a decent error in the predicted power consumption, an error of about 2.4 watts. That is good. But let's see how this is evolving. In this type of plots, what we see is the decisions or the actions taken through time from epoch to epoch, epoch 1, epoch 2, epoch 3, epoch 4, by an agent trained not to violate a specific power cap, in this case 52.5 watts. See that we evolve from mainly a random action decision at the beginning of the process to a process in which actions are taken so that the power is always close to 52.5 watts. In these graphs, what we are representing is power, and we see it is adapted quite well to the power cap. But what about actions? In this case, we see that actions are initially taken as random and evolve towards an action selection that is mainly around 1.6 gigahertz. That is exactly the frequency we saw is the ideal one for GMM, for matrix multiplications with this power cap. However, some problems with this naive environment, specifically in power cappings that are at the limit of the operating frequency of the processor. For example, for 97 watts, that is the power consumption typical for GMM running at the maximum frequency of the processor, we see that the average mean error is quite big in this case. Which is a problem here. The problem is that the system is learning how to put the processor at maximum frequency to attain 97 watts. But our action space forces the environment to apply always an action that is increasing or decreasing. In this case, it can only decrease frequency. The first modification in the action space is to add a third action that forces the environment to stay in the same frequency. The third modification of the third environment here is the implementation of non-uniform power intervals to the observation space. In both cases, the average error is quite good, not only in intermediate power cappings, but also in power cappings that are in the limits of the potential power dissipation for a given architecture. For example, in this case, for a power of 97 watts, we reduce the deviation of the first environment from around 10 watts to less than 1 watt or around 1 watt for the other environments. We have demonstrated that power capping and performance maximization can be carried out by means of automatic learning, adapting game learning infrastructures. There is, however, some future work that is interesting for us. Basically, this future work orbits around the use of hardware accelerators. Why using hardware accelerators? The inference obviously must be accurate, and we have demonstrated it can be in this case. But the inference must be applied in a fast manner and must not interfere with applications. If we use a GPU integrated in the system or use the CPU to apply inference, it's going to invalidate the learned results. So our solution is to use external accelerators. And we have two options here, GPU or DSAs. Which one is the most interesting? We have performed extensive experimentation on the use of GPU for both training and inferencing. For training, they are obviously the way to go. For inferencing, integrating a GPU into RLlib is not interesting in terms of performance. We have evaluated this for game learning, and GPUs are really not a good way to improve inference, but we have also integrated the use of an edge TPU on the inference process. And in this way, the inference time is reduced and attains significant speed ups, even though we are moving in the terms of milliseconds here to apply just one inference for different models in the RLlib infrastructure. So our goal here is to explore how the quantization process that is mandatory by the Edge TPU from Google implies a loss of quality in the extraction of the policy. We also want to transparently use the TPU, integrating it on the RLlib, and explore the use of multiple Edge TPU to solve or to cooperate solving the problem. All in all, we see that the power capping problem can be tackled by means of not only reinforcement learning, but also leveraging existing infrastructure, RLlib and GIM. We believe that both application and system level nodes can be considered isolated or in a cooperative fashion. We have realized that GPUs are mandatory for training, but not for inference, so that our proposal here is to train agents using GPU, but apply them by using DSA for faster inference and not to interfere with the current computations. Thank you, that's all.